Okay, so here for a CO3 minus 2 carbonate. All right. Oxygen gets what oxidation number? Minus 2, right? So this is a total of minus 6. This needs to add up to minus 2 since it has a charge on the polyatomic ion. And in that case, the carbon, what's its oxidation state going to be? It's going to be plus 4. Very good. Now, manganese for oxide here. Taking a look. What's the oxidation state on the oxygen? Well, it's minus 2 is the oxidation state for each oxygen. The total of them together would be minus 4. But whenever they're asking for an oxidation state of an element, you give it for that individual element, not the total. Okay, so yes, this would be minus 4 total. So that means that helps us figure out, because this should add up to 0. What is the manganese?
It has to be plus 4.
Plus 4, good. All right. Phosphorus pentachloride here. Now, if we're following our chart about the nonmetals, which one gets assigned the negative? The chloride does, because it's higher up on that chart. It's minus 1, right? Follows the halogens. So this is going to be a total of minus 5. So that means in this case, the phosphorus being less electronegative than chlorine gets assigned the positive value for the oxidation state, and that one happens to be plus 5. Okay? Now, sulfur tetrafluoride over here. What is going to be fluorine's oxidation state always? -1, most electronegative element on the table trumps everybody else, always gets the negative, okay? So in this case, that means sulfur is going to be
Plus 4.
plus 4, good.
Of course.
And on to potassium dichromate. Love this one, this is fun. I'll put it over here. We have our salt here with the polyatomic ion, so 3 elements to contend with. We have to figure out which ones we actually know here. Oxygen's a given. What's oxygen? -2. So this is going to total up to minus 14. It's going to add up to 0, right? What else do we know? Potassium or chromium here?
Potassium.
We know potassium. Alkali metals are always going to be what? Plus 1. Good. So this is going to be plus 2. So what goes in here? It's going to be a 12. But there's 2 of these, so we have to divide that by 2. So this is going to be,
Plus 6.
each individual one is a plus 6. Follow me so far? And for the last one here, I think this is called tetrabiosulfate. It's an interesting polyatomic ion. S4O6 minus 2. So that means this one has to add up to minus 2. Now, we know the oxygen's going to carry -2, and that's going to be minus 12 here. Okay?
Oh, this is the fraction.
Yes, so this has to be a plus 10, right? Okay, but there's 4 of them, so we need to turn it into the fraction, right? So each one is worth what?
5/2.
Plus 5/2. Very good. Interesting one there. So yes, you can have fractional ones. Not very frequently will you have a fractional one, but it is a possibility. Because remember, this is really just a record-keeping system.
Plus you.
Record-keeping system.
How's that physically possible? Have, like,
Okay, so are we good with assigning oxidation numbers? Yes.
So if it's just a record keeping system, so for example actually, yes, so for something like B, why can't we just set both elements to 0 or something?
What do you mean set them to 0? We're transferring electrons.
Okay.
So you have to keep record of what it's starting with and what it's ending with so you know which way it transfers.
Okay.
And that's what I mean by the record keeping system. Does that make sense?
Okay.
Okay. Because if you can't do the assigning oxidation states, like the rest of this is going to be a little challenging. Hopefully we're good with this. All right, now, you're given a reaction like this one. When powdered aluminum metal is mixed with pulverized iodine crystals, drops of water is added to help the reaction get started. The resulting reaction produces a great deal of energy, so it's exothermic. But mixture bursts into flame, purple smoke of the iodine vapor produces the excess iodine. So for the equation for the reaction is aluminum plus iodine gives you aluminum oxide. So here, basically after all that lovely setup, it's going to want you to assign the oxidation numbers, determine what is oxidized, what is reduced, and what the agents are. So, first thing in a problem like this is to assign oxidation numbers above the elements, just like it said in the rules. So, elemental aluminum gets a 0. Elemental iodine gets a 0. Now, in the compound, iodine's going to be -1, and aluminum's going to be +3. They follow their normal monatomic charges on the periodic table. Yay. So, aluminum goes from 0 to +3. What does that tell you?
It's raw.
Is it oxidized or is it reduced?
Oxidized.
This one's being oxidized. Good. And the iodine going from 0 to -1. This one's being reduced. Good. Now, in order to identify the agents, okay, you have to look at the entire reactant. It's not just the element. It is the entire reactant that contains that element. So, since aluminum is being oxidized, this reactant right here, okay, it is causing the reduction of the iodine. So therefore, this one would be your reducing agent. And it would be the aluminum there. Now, the iodine I2, okay, has to be I2, the entire thing, not just I2, the entire reactant. It is being reduced. So therefore, it's causing the oxidation of the aluminum. So this one is going to be your oxidizing agent. So it's the entire reactant that contains that particular element in it that is going to comprise the agent. Yes?
What about the coefficient and the state of matter? Do you need it?
We're just identifying, no, we don't need the coefficient or the state of matter here. We just need to identify the reactant. Okay? Yes, it takes 3 moles of iodine to make this reaction work, sure. But here, when we're just identifying the agent, we only just need the reactant. Okay?
So you can tell it's the reducing agent, like the aluminum is a reducing agent because it's oxidizing into...
Well, since aluminum's being oxidized, that means it's giving away electrons, right?
Right.
So it's causing the reduction of iodine.
So it has to be the reducing agent.
So it'd be the reducing agent because it's causing reduction.
Okay. So
Sort of
it's like
backwards.
opposite.
It is. It's like opposite each other, yes.
Okay.
Okay? Now, your turn. Try it. See what you come up with. Okay, so let's start assigning oxidation states here. I always quickly do all the elements. Get the elements out of the way. They get the zeros, right? That's easy. Oxygen's probably the next one to easily assign. So I get those out of the way. Then I look to, yeah, like lead is a multiple oxidation metal. So now I have to figure it out based off of what it's with. In this case, the lead is going to be +2 because it's +2 -2. Here, the sulfur is going to be a +4. We know this one's a +4 and +2 and +2. Now here for the PVS. In this case, what is the S going to have? It's going to follow its group 16 -2, and the lead being the metal will have the positive charge And that means it's going to be a +2.
Where do you get -2 from?
What?
Oh, sulfur's there.
You silly Billy.
Okay.
I thought sulfur was.
Yeah, sulfur's in group 16, so sulfur is going to follow the 16 non-metals. All right, that looks a little bit better. Now we can look for charge change or oxidation state change. So if I look up here, I see S going from -2 to +4. Okay, so -2 to +4. What does that mean?
Being small.
S is being oxidized, right? Okay, and what else is changing up there? The oxygen. 0, -2 in 2 places. Okay, you see that? So 0, -2, that means it's being reduced for the oxygen. Now for the agents. The agents can only be PBS and O2. So, PBS contains the sulfur that's being oxidized. So that means PBS is which agent? This one is the reducing agent. Very good. It's causing the reduction of the oxygen. And over here, the oxygen is being reduced, so therefore it's causing the oxidation of the sulfur. This one, of course, is the oxidizing agent. Top one. Now let's look at the next one. Oh, one other thing to comment on too before we move on. Notice how lead doesn't change its oxidation state. Right? We agree on that. It's +2 on both sides.
Yeah.
So technically lead is like a spectator. It's not participating in the redox. So in this case, if you want to think of lead as a spectator, you can think of that because it's not doing any of the redox. Not part of the reaction. So in a way, it's a spectator. All right, down below here, which ones are changing oxidation state? Lead's changing. Lead goes from +2 to 0, so that means lead is being,
Carbon is changing.
it's being reduced, right? And carbon, so carbon goes from +2 to +4. That means it's being oxidized. Okay, good. Now let's look at the agents. We have PbO and CO as our possibilities here. Since PbO contains lead that's being reduced, that means this one is the what? Oxidizing agent, good. It's causing the oxidation of the carbon. So carbon monoxide is being oxidized, so therefore it's causing the reduction of the lead. So this one's going to be your reducing agent. Good so far? Yes, yes.
I thought I got it. But now I
All right, one more practice, a combustion one. Check out combustion here as redox. Okay, so once again, assigning oxidation numbers, start with the elements, give them a 0. Next, oxygen's usually the easiest one to go with. Now, in covalent compounds, like propane here, C3H8, everything's a nonmetal. Hydrogen always gets assigned +1. Okay, +1. Because if you really think about it, hydrogen's over here on the left of the table, the top of the first column. So everything over to the right is going to be more electronegative than hydrogen. All those nonmetals to the side there. Okay, now, the only case hydrogen carries the -1 is if it's with a metal and it's a hydride. Once again, that's a very rare occasion. All right, so that means this is +1 as well. It's in the covalent compound here, all nonmetals. Here, carbon dioxide's pretty easy. We've already done this one a few times. That's +4. Now we're going to get a fractional one for the C in propane. Because this is going to be +8. So we need this to be -8. How do we make that one be -8?
Fraction.
Fraction. Negative what? 8/3?
Yep.
Alright, so now we have our oxidation numbers assigned. We can look at which elements are being oxidized, which elements being reduced. So O is going from 0 to -2, 2 places. That means oxygen is reduced, good. And the carbon going from a negative, what, 8/3 to a +4, increasing in oxidation state, so that means oxidized for the carbon. So propane then, which agent is propane going to be?
Reducing agent.
Reducing agent, good, because it's causing the reduction of the oxygen. And then the oxygen is going to be the oxidizing agent because it's causing the oxidation of the carbon. Good.